So today we are going to do chapter 7, which has mainly to do with energy and conversely work. So let's go ahead and get into this. So energy is a scalar quantity. It's basically the same as like mass. It's a measurable unit that doesn't have a direction assigned to it. So it's a scalar. It is always conserved, just like everything in physics, basically, meaning that we need to account for all of it all the time. I think they use like a banking example here, like you have so much money that comes in, so you have to account for that money, then only that much money can go out. So I use a lot of water analogies. So if you have like a water tank and there's so much water in it, then you only have that much water. Works well for electricity too, not that we're going to get into that here, but so kinetic energy. So there is a difference between kinetic energy and potential energy. In this chapter, we only get into kinetic energy when you do the lab for the spring, the gravitational stuff with the spring. You're going to get into potential energy also. Potential energy is just the potential to do something. So it means it has some form of stored energy. Kinetic means it's actively moving. It's actively using the energy it has. So if I were to take an object here, move it upwards, I have increased its gravitational potential energy. Because when it's lower, it only has so much energy before, like the potential to drop it to the ground, it has X amount of energy. If I take it and I raise it up, then it has however much more energy than it had before. It'll have more energy when it impacts the ground if I drop it. So by me picking it up and doing work on the system, and these are some terms we'll get into here in a minute, I'm putting energy in the system. The energy is still conserved. I put more energy into the system by raising it up, if that makes sense. Hopefully your lab instructor goes over that more. We'll see. Who knows? So, like the statement says, kinetic energy is 0 for a stationary object. It has to be moving, and we use what is commonly phrased as an approximation because it's based off Newtonian mechanics. It's 1/2 mv squared, so it is a almost perfect approximation as long as you're well below the speed of light. When they say well below the speed of light, even if you get up to like a quarter the speed of light or so, it's not terrible. So basically anything that is moving within our world that we deal with every day is well within this range. Even probably one of the fastest moving objects we have is a space shuttle moving around the planet, moves something around 25,000 miles per hour. That's well within the confines of this. It's still going to work. The units of measurement we're using for kinetic energy is joules. Joules is energy, therefore that's just what it is. I think they get into later, there's a British foot pound or something. Engineers may use that. They use a lot of the British units. So here's an example. Two balls of equal size are dropped from the same height. One ball has twice the mass of the other. When the balls reach the ground, how do the kinetic energies of the two balls compare? Well, if we go back and we look at the formula, well, you have a mass in here, right? So it said that the one is twice the mass of the other one, therefore one is going to be 1/2 mv squared, and the other one's just going to be mv squared, right? So it's going to have twice the kinetic energy. So the lighter one, which they're all the lighter one, then has half, which is B. Okay, so some of the equations we get into here. I'm going to look at the energy released by two colliding trains within given weight and acceleration from rest. It's an example problem in the book. They have the details of the acceleration and the weight in there. It says it's given. This is the portion, that's the acceleration that's given. This is the distance that's given. I believe it's double the distance because it's two trains moving head on and they're going to collide with one another. So they've just taken half the distance for one train, right? One train goes half, the other train goes the other half. And then they start from rest, so the initial velocity is 0 here. So it becomes a pretty simple equation, plug and chug, and then you just get this answer of 147 kilometers per hour. From here, we can reverse engineer and find the mass because we have the weight. The weight is the mass times the gravity, so if we just divide the gravity out, we're left with just the mass. So now we have the mass and the velocity, and we can figure out the kinetic energy. So putting in the answer, you get 2 times 10 to the 8 joules. So we've gone over energy. What is work? The definition is given here. In a transfer of energy via a force, work is done on the object by the force. So this more specific definition here, work, which is represented by W, is energy transferred to or from an object by means of a force acting on an object. Right? So, and then it wants to differentiate between positive and negative work. Energy transferred to an object is positive work. Energy transferred from an object is negative work. And this comes back to sort of along the lines of choosing your coordinate system. You also have to choose the body and the system that are doing work and being worked on. So this can change a problem drastically depending on which you choose. But for most physics textbook problems, it's fairly obvious which one is which. Okay, so some examples there. It's not important. So when we look at this, and there's nothing defined by this, work is force times distance. Some force times some distance. The other portion of this, there's a cosine in there. And they're using phi, so we use phi. So you have force times distance and the cosine portion of this. So if this is it says it's a bead. I think the example in the book is used as a bead that's being pushed across some wire. We look, where's the work being done? So the work is only happening in the x-axis. So if we look at the y-axis, it's not moving up or down. So no work's being done in the y-axis. That's sort of the conceptual portion of it. If you need a more analytical way of figuring it out, because perhaps you're doing a problem that it isn't explained what's happening, you just basically plug in the components of the angle. Right, so if you plug in the y component of this, it's 90 degrees, you put this in for cosine, and then it becomes 0. Right, so that zeroes out the work being done here analytically by putting in the angles. So the other way is just the angle 0, then cosine's 1, so it's force times distance. Over here, they're talking about the difference of the energies. So you have a small initial kinetic energy, and then you can break it up into the components again because it's working at an angle. It's saying the force does a positive work on the bead. It's increasing the speed and the kinetic energy of the bead. And then you have a larger final kinetic energy. And it has some displacement between the initial, which is over here, and the final, which was over here. So you have a kinetic final and a kinetic initial. And we'll get more into that. And then, yeah, here's your British foot-pounds. So if we look at the equations again, and we go through the same thing that we just explained, we have this equation again, your basic kinematic equation that we learned a while ago, and your Newton's second law that we constantly use. If you rearrange these using the same methods to find out the kinetic energy for it, you're basically going to get a kinetic energy final and a kinetic energy initial. So what we're saying is, with a lot of these problems, right, it's just the kinetic final minus the kinetic initial, and that's going to equal the work, right? So you're going to have some force times distance, which is the work. So therefore, the kinetic final minus the kinetic initial equals work. If kinetic final equals 0 and kinetic initial equals 0, then it's just the work equals 0, right? And we'll get into some situations with that. It'll make more sense here in a minute. Okay, so definition at the top. The definitions are pretty important. To calculate the work a force does on an object as the object moves through some displacement, we use only the force component along the object's displacement. So this is going back to this equation that has this cosine in it, basically saying that if you're pushing something in the x, then in the y, if it's being at an angle like the bead on the wire, we're only taking the x component. That's the only important part of it, right? The y component is not contributing to the work being done. The components that are perpendicular to the system, again, the y, does zero work, right? It's not contributing to the work being done. So we have the vectors involved here. You have the force and the distance, which are both vectors. And it has some notes here. Object is particle, not a liquid or something. Work can be both positive and negative, depending on how it's being worked on. Okay, so a force does positive work when it has a vector component in the same direction as the displacement. So basically, they're moving in the same direction. It has a negative vector component when it's working in the opposite direction, and we'll get into some examples of that too. So then we're talking about the net work done. So again, just like your summation of forces acting in one direction versus the other. Same thing with the work. You're going to sum up the work done. Work going in one direction versus work going in the other direction. You have to subtract them to see which way the work's being done. Okay, and it's more of what I just said. Another conceptual example, some children are practicing catching baseballs. Coach tosses the ball into the air and hits the ball with his bat. The ball travels nearly horizontally, directly at the shortstop, who manages to catch the line drive. Did the coach, via the bat, do any work on the ball it was hit? So they're giving you a piece of information there. It was hit nearly horizontally, right? So basically saying no y component, not really at an angle, it's just going straight at an x. We'll go this way, straight at an x, not at an angle, right? So most of the energy is put directly into it. You're not wasting it from it going at an arc, somehow going up and down. And we have, did the coach via the bat do work on the ball as it was hit? So basically you have to ask yourself, what is it? The equation for the work is the force times the distance. If we take the cosine theta component, the angular component, we know it was traveling mostly horizontally. So was there a force applied? Yes. He hit it with the bat, right? Was there a distance traveled? Yes, there was. So there must be work being done on the ball. And yes, work was done on the ball because during the time the force acted on the ball, the bat and the ball moved through some distance. Just seems yes. The only other yes is here. Work was done on the ball because the force of gravity was acting on the ball while it was being hit. We're not looking at the y components, so no. So the work kinetic energy theorem. This is a pretty big theorem that comes up over and over again. Even for me when I was in grad school, the math gets harder, it gets more complicated, you have more factors involved, but still someone can refer to the work kinetic energy theorem, and it's still this basic thing that we're talking about here. So pretty important foundational theory. And as I displayed earlier, I wrote out like the kinetic final and the kinetic initial. This equals the work, right? So the change in kinetic energy. So there must be a change in kinetic energy for there to be work done. And of course, you can rearrange it to solve for different pieces depending on what you're looking for, etc. in a problem. Positive and negative work. They give not really an example, just a kind of a numerical example. If the kinetic energy of a particle is initially 5 joules, a net transfer of 2 joules to the particle is then added. It's positive. You get 7 joules, so it's positive work done. A net transfer of 2 joules from the particle, and now it is negative because we have subtracted them. I'm going to give you another conceptual example of this, and you won't actually go over this unless you do 182, but I think it's a good example that's used a lot in 182. It's a similar system in all the problems in 182. So you have basically some closed box. And then you have some kind of like mechanical press, right? So you have some kind of motor over here. It's going to push this thing. So it's moving this direction and it's going to compress whatever's in here. Well, if there's some gas in here, right, you're choosing what's going on here. So you're saying the system and the body, right? So the system is the entire apparatus with inside the box. You got a motor with a press on it, and then you have some gas in there. So the body that we're acting on is then the gas. So if I compress this and we push it over, I'll try to draw this quicker, so that it's over here now. And now our gas is compressed and more dense. Basically, that's the system doing work on the body, right? So this is from an outside perspective. Now, the other way you can do this when the body does work on the system, going the other way, so the difference between adding and subtracting, is then you have the same situation, but now you have the press wherever it initially starts, and you have the gas, only let's say I can't really draw a fire. We'll say that's hopefully you can see that. All right, I don't know if that looks anything like a fire, but say you added heat to the system. We put a fire around this box. It's not insulated, so you're adding heat to the system. The system gets warm, therefore the gas expands, right? And it starts pushing on the press, right? So instead of the press pushing in on the gas, now the gas is getting hot, it's expanding, it pushes the press back out. This would be an instance of the body doing work on the system, right? This is going in the opposite direction. Again, so this is an example out of like thermodynamics and 182 stuff, but I think it's an easy conceptual thing that you can deal with, and it makes sense, other than just writing 5 and 2. Okay, so we went over this. We have our equation, mgd. That's just your mass times acceleration. So that's your force, right? And then that's just times distance. And then you have the cosine portion. So you're going to see mgd a lot, right? It's going to be used in a lot of examples, a lot of problems. So you'll get used to seeing just mgd instead of f times d, etc. So for rising object and a falling object, so if you have, for instance, a ball going up versus a ball going down, what they're doing is we're only dealing with the vertical components here, so you're turning the axis so that it is 90 degrees the other way. So now we can still do it in the x. We'll just say we've turned the whole thing, or you could just say you're technically dealing in the y, but we'll say we've turned the coordinate system 90 degrees, so now that the x goes up and down. So when we look at this, when you go, depending on your starting point and how you set up the problem, you're going to have now 0 degrees and 180 degrees. Because of your normal x-axis, you're going to start with like 0, go all the way over to 180. But now we've just turned it so that it's vertical, right? So it's still going from 0 to 180 because that's the direction that the action's happening in, and that's the direction we want to deal in, right? So we're adding up the components that are in the direction that we're dealing with. So basically, it's just saying that the cosine turns it into negative, cosine turns it into positive. That's all. Work done in lifting or lowering an object, applying an upwards force. Okay, so I kind of initially went over this. We have a kinetic final. We have a kinetic initial. If these things equal the same thing, then it ends up being 0. In this case, we're saying two different works being, you have some kind of work applied, and this is also an example in the book, I believe, and this is just some kind of applied work, and then this is gravitational work being done. And we're saying that if the applied work and the gravitational work are the same, then it equals 0. Therefore, the applied work must equal the negative of the gravitational work. And this is fairly obvious, right? But what they're telling you is to remember this portion, because when you do problems, this is a way of getting information. It's sort of like the normal force and the gravitational force. So if you have some block, again, you have some n working up, and then you have some gravity working down, an mg. So if you know the mass of something, you can multiply it by gravity and figure out the normal force, right, is what they're saying. So if you know one of these, you could figure out the other one, a similar thing. Okay, so and then it's regardless of the path that it takes. Do they give an example of that in here? I think in the book they give a similar example where they say, like, basically if you take a book and it's sitting on the ground and then you pick it up and you put it on the top shelf, basically the kinetic energy initial is 0 on the floor, and then at its final state on the shelf, its kinetic energy is still 0. So we're saying work has been done, but the work ended up canceling out because the applied work that you're using to pick up the book versus the gravitational work that's pulling down on it. So essentially no net work was done by the end of the problem. You'll notice in these problems that it depends on the exact situation you're looking at. So we've labeled our initial and final as the floor and the shelf. If you change that and you just picked it up initially and it's in your hand and you're looking at the situation where you're raising it up to the shelf, that's different. There's going to be a total network done instead of the network equaling 0. But the moment you stop moving, now kinetic energy is 0, and therefore if it started from 0, then the work being done is 0. So it's very particular to the situation you have to pay attention to. And then again, the path being regardless again. If I pick up the book and I put it on the shelf, if I pick up the book and I go all the way around like this and go crazy with it and then put it on the shelf, it went the same distance, right? It's similar to the vector problems you did where something would go like up and then it would go east this amount and south this amount and whatever. All you do is end up drawing that displacement vector at the end, and that's the total distance it traveled. Similar thing. Okay, so again, we're saying upward displacement, something's moving upward. You're doing positive work this direction, negative work in this direction. So again, this is just saying more of what I said earlier. You have, depending on going up or downward, whether it's actually being displaced some distance d. And then this is talking about, there's a 716, I think is an equation. They need not be equal. And then it's talking about how basically the initial and the final energy, you need to know the difference to know whether it's doing work at the end, the total network. Again, same thing I already talked about. Okay, an elevator supported by a single cable descends a shaft at a constant speed. This is important here, and there's a written example in the book, and there's different situations. So these are going to seem like very similar problems, but they differ slightly in the wording, which completely changes the problem. I believe the one in the book says something about the wire holding the elevator slips, and therefore it's suddenly accelerating. This is moving at a constant speed, so it's not slipping, right? So there's no acceleration. It's just moving at a constant speed. So the only forces acting on the elevator are the tension in the cable and the gravitational force. So tension pulling up, gravitational pulling down. It's not accelerating, therefore they must equal each other, right? So it has to be 0 joules. We know that. I still haven't figured out why that automatically draws a line. So it's supposed to be 0 joules. We have 3 answers that say 0 joules. The work done by the tension force is 0 joules. this would mean that the gravitational work is whatever it is, and that's going to be the total amount of work done. We already said that the net work has to be 0 because they equal each other going up and down. Then the work done with the gravitational, just the opposite. So yeah, it has to be B. And again, here's some more examples from the book. They give this example, and these are gone out in full detail. You can look in the book, and they're given numerical answers, and they run through the formulas and show exactly how it's done. So I'm not going to go over that part, but basically we're saying here, sand is being pulled up a ski slope by a reindeer. We're saying the tension does positive work and gravity does negative work. And here's this situation again, this free body diagram down here. Again, I told you this is going to keep coming back up. So hopefully you worked out the geometry and you understand how this thing works. Similar problems is they're just going to keep coming up. So do not just sweep this under the rug and say, I don't need to know this right now, or I'll figure it out later, or it was only one problem. It doesn't matter if I need to know it. This is a constant thing. Okay, so make sure you know how the angles and where we're getting FG from, and mg cos theta, mg sine theta, the components, etc. So it's being pulled up, right? So it's moving upward. So we're saying that the magnitude of this force is greater than the magnitude of this force. This is a component of the gravitational force pulling down, but we only want to look in this direction, right? Because this direction, moving up and down, you have the normal force and the cosine component of the gravitational force, and it's not moving. It's not moving in that direction. So if we're slanted, if we're from Santa's perspective looking up, we're not moving up or down, right? We're only moving forward and back. So you're looking at the tension and the mg sine theta, where you have tension minus mg sine theta, and the mg sine theta must be less than the tension. And some of the points here is we're saying that the tension is doing positive work and the gravity is doing negative work. I think in the book specifically for this problem, again, you have to be careful how it's worded. They say that this thing starts at rest and it ends at rest. So don't be confused when you look through the problem and you're like, well, what the heck, the tension, these two forces are clearly different. The tension force is greater than the gravitational force pulling it down, but they're looking purely at the beginning spot and the end spot, right? You can see my cat, he came to help. So yes, while it's moving, there's work being done, and the tension minus the mg sine theta do not equal each other, therefore it equals something. The problem is that when it gets to the top, it's no longer moving, right? So again, just a way of wording it. Again, elevator system, we have a couple different elevator examples here. In this case, you're just a passenger in the elevator. Elevator's functioning normally as it should. You're moving just at a constant velocity. So the tension pulling up, you have some tension pulling this direction, some gravity pulling this direction. They must equal each other, right? You're moving at constant velocity, you're not accelerating. In the book problem, that thing slips, right? So all of a sudden when it slips, then you have the tension still same as it was, only now your gravity component is, the magnitude of it is going to be much greater, because now you're suddenly going to be accelerating. It's a force acting on it. So the end result is that there's work that's been done to it. Now, if you were looked at the initial situation where you got on the elevator and the final position where it crashes into the ground, kinetic energy is 0 in both cases, and then you say no work's done. So you got to be careful which parts you're looking at. Okay, so again, keeping with the calculus portion of this, kind of adding this part, and there's some more, more thorough into the math and stuff in the book. You can go through that, but hopefully you've learned by now what an integral is. Hopefully. So if we plot our variables, so if you notice, this is f of x, right? So that's a force, and then we have x. So we have force and we have a distance, right? Force times distance, we're dealing with work all over again here. And the way you can figure this out is by integrating, And what integrating is doing is summing up the area under the curve, right? If you've had this in math before, you should have heard that phrase used. You're just summing up the area under the curve. And they love to go through the history of this. I think it's a good way of explaining it. But you have this system where basically you're taking some distance x, and you're saying, okay, boop, boop, boop. If you ever have Dr. Kwong, he loves to tell the story of his PhD qualifying questions. He was given some complex integral and he had no idea how to solve it. Therefore, he just plotted it, right? He plotted some line, and then he figured out by doing an approximation, basically, what the area was under the curve. And the approximation that he got is close enough to the answer he would have got for the integral. And so from a physicist's perspective, you got the answer, right? So it didn't really matter how you got there. The path traveled doesn't matter. So if I were to take giant blocks, like so, just in case you haven't seen this in calculus, and my giant blocks are kind of awful. I'm going to learn how to write better on this thing one day. This is an approximation. It's just not a very good approximation. So if we go down to B, we can see we make the blocks smaller, and this provides a better approximation, right? We make them even smaller in C, better approximation. So what they did was they said, theoretically, if we just keep going and you go to an infinitesimally small x, you should get the perfect answer. It's no longer an approximation. It's an exact answer, right? That's what dx is, right? In case you weren't taught this in math, dx is just the infinitesimally small distance of whatever variable you're using, right? So in this case, we're using x, so it's dx. So a dx is an infinitesimally small piece of what you're looking at underneath the curve. So we've gotten smaller and smaller until we got dx. That's what it is. Okay, so there's your math calculus integral review, hopefully. Okay, so I think this is, we have the integral form here, just kind of doing the actual working out of it. So if you're doing an integral, you're doing it, you're multiplying the force, and then the thing you're integrating is dx, right? This is the infinitesimally small x that we want to use, and then you're doing it from these bounds, right? You're doing it, you have x final and x initial. So when you go to do these, you're end up subtracting them. That's giving you the distance, right? So you're doing this basically force times distance over some distance. That's what's giving you the pieces. So then down here, again, they're just saying we're taking the components. So if it's a 3D system, whatever's, it'd be very complicated, right? So you have to do like these three integrals to solve it for each individual. Because again, we want to make things simple, put them in one dimension, solve them one at a time. Work done by a spring force. Okay, so you're gonna do the spring lab, and I think I posted some stuff already, some YouTube videos and stuff that are explaining what you go over in the lab, the difference between transferring these energies between kinetic and potential. Earlier when I spoke, I said that there's some kinetic energy, something moving, and then if I, for instance, drop a ball, it has some kinetic energy and then it stops on the floor. If I take the ball, I pick it back up and I put it on a shelf or whatever, it has some gravitational potential energy. It has the potential to fall off the shelf and of its own accord fall to the ground. You're going to get into something else in the lab called spring potential energy. So basically a spring is this distance apart, it's whatever, you take both ends, you pull it, it wants to go back to where it was. So when I let it go, it shrinks back to whatever the original length was, its natural resting state. So one of the things that we do when we use springs is it doesn't matter if I compress it. If I compress it, it wants to go back to where it was. If I expand it, it wants to go back to where it was. So what we say is this is like a restoring force, right? The spring has a restoring force. It has a natural state that it wants to be in, and as you expand it or compress it, it wants to still go back to that. So this is what they're saying. They're saying that the A is the relaxed state here. That's the instance over here. So nothing's being applied to it. It's just naturally sitting there. It has a block attached to it. When you pull the box away, you've expanded the spring. Therefore, it has a restoring force that wants to pull it back to where it was. If you compress the spring, same thing. It wants to restore itself and go back. Yeah, so it's similar to the gravitational thing where when you compress it, it naturally, of its own accord, wants to go back somewhere. So if you take a spring and you lock it, for instance, in the lab, like you would have done if you were there. I don't know if you were there or not for your particular lab, but the projectile motion problem where you have the ball, you compress that ball with a spring. You push the spring back, it locks, you have the ball in place, you hit the button, it releases the spring and shoots the ball. So when you compress that spring, you put work into the system, then that work was basically stored in the form of energy, and in this case it is spring potential energy, right? It's the same thing as picking something up and putting it on a shelf, same concept. So you can have spring potential energy, you can have gravitational potential energy, you can have chemical potential energy. So if you have two chemicals, you mix them together, there's a reaction. Could be like exothermic, it's giving off heat, etc. It's another form of potential energy. So that's the difference between these energies that we're talking about. Just to go over the lab real quick, because I'm going to send this out to my lab classes too. If you take a spring, and in the lab what you would have had is a spring bouncing vertically like this, and you take some mass and you put it on the bottom. When you, if it's going to sit at its natural, whatever natural place. Everything I have is black and I'm wearing a black shirt, so it's not easy to see what I'm holding. But it has a natural resting place, so if you pick up the mass, all of a sudden now it has gravitational potential energy, but you've also compressed the spring, right? So now it has spring potential energy. So it has two different potential energies that are adding up for the total energy of the system. That's all the energy in the system. That's all of it, right? So when you let it go, it's going to bounce down further than it was before and then bounce back up, right? And then keep going until it loses its energy to heat, friction, sound, resistance, and air, all these little things. We're going to slow it down eventually so it comes back to a resting place. Just keep in mind that when the difference between the top and the bottom are very different, right? So the top is you have complete compressed spring energy. You have total gravitational potential energy at the top. When it gets all the way to the bottom, you've released all the gravitational potential energy. It is at its lowest potential point. It will not go any lower than that. Therefore, the potential gravity, potential energy of the gravity is now zero. However, the normal place it wants to sit is here. So when you're down here, all of a sudden now your spring potential energy is the same as it was at the top, right? Because you've separated a distance equally. Compressed, expand. It's still the distance between them should be roughly the same, at least for your first bounce. Theoretically, if we're doing it with no air resistance, everything book problem, then there is no change. There's no difference. They are identical. So the place that's in the middle, which this is a question that'll come up, you have to look at and you have to analyze. So now if we look at it in the middle, this is the place where it should have naturally been resting. So it has some gravitational potential energy, right? We had full gravitational here. We'll say it's half here. Then all the way at the bottom is zero. So now at the top we knew we had, we'll say it's 1. It's just the numerical answer for the spring potential energy is 1. The numerical answer for the gravitational potential energy is 1. So you have 1 and 1, you have a total of 2 energy. When it goes all the way down to the bottom, gravity now equals 0. Spring is equal distance away, so now it equals 1, right? So when you come back up, now you're in the middle, you have the gravitational portion halfway up, so now it equals like a half, right, of what it was. So you have to figure out where the energy is going, right? What's the other piece you're missing? You haven't included any kinetic energy. So at the top and the bottom of the system, it's not moving, right? So, and the way we account for that is it should actually bounce further because you have the two energies. Therefore, the spring energy has to be larger. But it's not moving either way, right? Okay, so that's a whole lab thing. Hopefully you go over it with your lab instructor. Hopefully I don't confuse you with whatever they may say. But if you have questions about it, just email me. So basically what we're looking at here is Hooke's law. So you can see this is very similar to what it was before. This is very similar to a lot of equations that we use. There's some constant. In this case, it's k. And then we have this distance d that something's traveled. The k is a constant that is specific to the spring that's used. It is an inherent variable that is specific to an exact spring. So if I took 3 identical springs, and you would do this in the lab, right? So you would have your group, the group next to you, and the other group. You all have 3 different springs. Depending on the wear and tear over the years of the spring, how often it's been used, if it's been stretched too far, these kind of things, it changes the K within the spring because the K is inherent of the actual spring you're using, right? So if I have like a little tiny spring, little tiny metal wires, it has whatever K. If I beef up the spring and now all of a sudden it's like this round all the way around, like say if you've ever seen like a shock on a car or something, it's the diameter of it's very big, right? That's gonna have a very different K than a little tiny one that's like we'll say the size of the notebook I have here, right? You have this little tiny wire going around. We'll say this is a spring. This is going to have a very different one than the shocks in your car, right? Because it's going to be a much bigger diameter of the wire going around, essentially. Okay, so the K is different for every spring. It's just something that has to be measured, basically, and it can change over time. So again, we're saying it's negative because it's a restoring force. It wants to go back to where it was. And then you have this Kx down here. So the common form of Hooke's law is the minus Kx. Work done. So the work done, again, we're taking the force, which we just labeled. This is f of x. F of x equals minus kx. When you do the integral, you want to put that kx in here, right? So you're doing the integral of, and we want to get rid of the negative sign, so we just add that there. So it becomes this integral of kx dx, and between x final and x initial. Right, so we're doing the integral, you have x, so it becomes squared divided by 2, if you follow how you do integrals. That's where this comes from, right? So when you integrate this, you get this answer total, right? So you get the 1/2 kx squared. When we put in the values, we have the final and the initial. So you take one and you subtract it from the other, and it should be the other way around. I guess they left the negative sign in there. So yeah, so normally you have the final minus the initial. That's where the 1/2 and the squared came from because it was integrated. Okay, so again, the work could be positive or negative. It depends on which one's larger, etc. We went over this. Work WS of spring is positive if the block ends up closer to the relaxed position. Okay, so it's saying basically if a block's resting point is here and it's attached to a wall over here and you pull it out, when you let it go, if it starts to slide towards it, it's doing positive because it's going back to where it wants. If it hits the part where it wants to rest and keeps going, now it's become negative, right? But then it's going to stop and the spring's going to compress it again and it's going to go back this way, so then it's positive. So they're just differentiating between the positive and the negative. Okay, so then same deal. You have the 1/2 kx squared. It's your energy of your spring. And then we have applied force. Again, same thing, final and initial, same deal we went over. If you know one, it's the negative of the other one. And this is the same thing I just explained a minute ago. Okay, block A has a mass m and a block B has a mass of 2m. Block A is pressed against a spring. To compress the spring by some distance x is then released such that the block eventually separates from the spring and slides across whatever surface it's on. But you have a frictional force acting against it, right? You have some coefficient of kinetic friction here, the mu k. And then you do the same thing with block B, which has twice the mass. So basically we're saying you have, where's my mouse? You have some spring force, we'll call it F sub s, spring force acting in this direction. Remember that the frictional force always acts against the direction of motion. So you have some frictional force acting this way. So if you remember, the frictional force equals mu n. And so if we take that and we make it mg, well, you have block 1 equals mg, and then block 2 would then equal mu 2 mg. Right, so the frictional force acting on the one that's twice as heavy is twice as much. So for the block that is 2m, we can say will go a half as far, or the lighter one will go twice as far. So these are all in terms of block A. So like I said, block A goes twice as far. Slides same distance, half distance, twice distance here. I believe that should be the answer. Okay, power. So power is basically a measure of work done. And power is done just work divided by time. How much work was done over some specified period of time. And your electric bill basically runs like this, right? How much power did you use? How many joules are you using over some time? And so that's what we're saying here. You have joules per second. That is work, or power. And this is measured in watts, not to be confused with work. So this is work, but power, the unit or power is in the units of watts. So don't get these W's confixed. They're different W's. So yeah, and then they give the example here that in your house, for instance, it's measured in kilowatt hours. So it's how many kilowatts you are using per hour. So how many thousands of watts unit of power are you using per hour? And then we're just finding the instantaneous power at a particular time. They're saying then we're just differentiating. So remember, this is just basically the change in work over the change in time. So if we look at this, we have the power equals the change in work over the change in time. We can explicitly say that work equals force times the cosine of whatever angle times the change in x, right? We put that over dt. We see now that we have dx over dt, so we can isolate these. And then just say that if we multiply the force times the cosine over dx over dt, we've seen this before. So we know that dx over dt equals velocity, right? Take the derivative of x in respect to time, you're going to get velocity. So what we're basically saying is now we have the cosine component of the velocity. Therefore, we can say that power is force times velocity. It's the same thing. A little checkpoint thing here. A block moves with uniform circular motion because a cord tied to the block is anchored at the center of a circle. Is the power due to the force on the block from the cord positive, negative, or zero? So you have some anchored point that doesn't move and some block spinning around it at the end of some rope. Again, if we go back to our circular stuff and we stop it at any one point, you have the point here. It's going in the velocity this direction, but the acceleration is moving inward, right? So it's perpendicular to the velocity over here. Therefore, that we're saying the angle is 90 degrees. So it has to be 0, is what this is saying. It's kind of a weird example. I don't know if that helps, but you could do the math and prove it to yourself anyway. I don't know if it helps conceptually. And that is it for now. Summary of the forces. In case you guys are ever wondering, the end of the chapter thing where it sums up things is a really good place. Again, we don't have tests in class, so it's a great way to study for tests or to make note cards if you're in a class where you need note cards. And most textbooks have it, so I would use it. But yeah, let me know if you have questions.